Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Welcome to our technical talk show. Today, we'll explore electrocatalysts and their role in renewable energy storage. Electrocatalysts are crucial for water splitting and hydrogen production, a key technology for decarbonization. We'll discuss challenges in finding efficient and cost-effective electrocatalysts and how machine learning is accelerating their discovery and design. Our focus will be on the implications for the future of renewable energy storage, including wider adoption and reduced greenhouse gas emissions. Could you explain the importance of electrocatalysts in the context of renewable energy storage, particularly regarding their role in facilitating electrochemical reactions?
Electrocatalysts are like helpful little friends that speed up important chemical reactions, much like how a coach helps a team play better. In the context of renewable energy storage, electrocatalysts play a crucial role in making processes like converting water into hydrogen and oxygen happen more efficiently. Imagine you have a big jar of water, and you want to split it into two parts, hydrogen and oxygen. This is an important step for creating energy that can be stored and used later, like saving your favorite dessert for later. However, splitting water isn't easy. It requires some help to make it happen quickly and effectively. That's where electrocatalysts come in. These electrocatalysts work by providing a special surface where the molecules can gather and interact. When the molecules meet this surface, they react faster, almost like how a smooth slide helps kids go down quickly. But there's a catch. For this process to be used widely, we need electrocatalysts that are both effective and cheap, just like how we want to find a fun toy that doesn't cost a lot. If we can find or design better electrocatalysts, we can help make renewable energy storage more accessible and efficient, storing energy from sources like wind and solar power for future use. In summary, electrocatalysts are essential because they help speed up the chemical reactions needed for renewable energy storage, making it easier and more cost-effective for everyone.
What specific challenges do researchers face in finding low-cost and efficient electrocatalysts for these electrochemical reactions? And how do these challenges impact the scalability of renewable energy solutions?
Researchers face several challenges when it comes to finding low-cost and efficient electrocatalysts for electrochemical reactions, which are essential for renewable energy solutions. One significant challenge is the reliance on expensive and rare metals, like platinum, for current electrocatalysts. These noble metals are like precious gems that are not only costly, but also limited in supply. If we want to make energy storage technologies affordable and widely available, we need to find alternatives that don't break the bank. Another hurdle is the complexity of the chemical reactions involved. The process is required to convert renewable energy into fuels, like hydrogen or methane, can be quite intricate, much like trying to solve a complicated puzzle. Researchers often use advanced computational simulations to model how different materials can behave as electrocatalysts. However, these simulations can be very resource-intensive and slow, limiting the number of materials they can test. It's similar to having a long line at a candy shop. Only a few kids can get in at a time to choose their favorite treats. The impact of these challenges on the scalability of renewable energy solutions is significant. If we can't find cheap, efficient, and durable electrocatalysts, it will slow down the progress in developing technologies that can store renewable energy effectively. This means we might struggle to meet growing energy demands and reduce our reliance on fossil fuels. In summary, researchers must overcome the issues of cost, resource limitations, and complex reactions in order to develop effective electrocatalysts that can enable widespread use of renewable energy technology.
In light of these challenges, how does the application of machine learning contribute to the identification and design of more effective electrocatalysts? And what advantages does it offer compared to traditional methods?
Machine learning plays a significant role in helping researchers identify and design more effective electrocatalysts by addressing the challenges that traditional methods face. One of the primary advantages of machine learning is its ability to process and analyze vast amounts of data quickly. Think of it like having a super smart assistant who can sift through a mountain of information in no time to find the best solutions. In this case, machine learning can efficiently approximate complex calculations that are normally performed through expensive and time-consuming quantum mechanical simulations. This means researchers can explore a wider range of materials and configurations for electrocatalysts without getting stuck on just a few expensive tests. Additionally, machine learning models can help predict how different materials will behave in chemical reactions. This is similar to how a magician can predict the outcome of a trick based on their knowledge and experience. By training these models with data from previous experiments, researchers can gain insights into which materials might work best, leading them to new and potentially cheaper alternatives to precious metals. Moreover, using machine learning can accelerate the design process of electrocatalysts. Instead of relying on trial and error, which can be slow and costly, machine learning can provide researchers with informed guesses about which properties to focus on, like efficiency, reaction rate, stability, and selectivity. In summary, machine learning offers a faster and more effective way to identify and design electrocatalysts compared to traditional methods, ultimately helping to overcome the barriers to scalable renewable energy solutions.
Could you elaborate on how the Open Catalyst Project OC20 dataset specifically aids in the machine learning process for electrocatalyst design, and what kind of data it provides for model training?
The Open Catalyst Project OC20 dataset is a valuable resource that supports the machine learning process for electrocatalyst design by providing a rich set of data needed for training models. This dataset includes information derived from quantum mechanical simulations, specifically focusing on the interactions between catalysts and adsorbates, the molecules that attach to the catalyst surface during reactions. Imagine it as a big library filled with different books, where each book contains details about how various catalysts behave with different molecules. This library enables researchers to learn and predict how new catalysts might work without having to test each one in the lab, which can be time-consuming and expensive. Moreover, the OC20 dataset captures a wide array of potential combinations of metals and their configurations, reflecting the diverse possibilities in catalyst design. This is like having a huge recipe book that contains thousands of different ways to make a cake. Instead of trying to bake each cake individually, researchers can use the dataset to find the best recipes and optimize their ingredients quickly. In addition, the dataset provides the necessary foundation for training machine learning models to approximate complex calculations, such as those performed by density functional theory, DFT. These approximations are helpful because they allow researchers to explore many more catalyst designs efficiently. It's similar to using shortcuts in a maze. Instead of wandering through every path, you have a map that shows the quickest route. In summary, the Open Catalyst Project OC20 dataset aids in machine learning for electrocatalyst design by supplying extensive data on catalyst behavior, enabling efficient exploration of new materials, and allowing researchers to develop more accurate predictive models. This ultimately helps in identifying effective electrocatalysts faster and at a lower cost.
What implications does the successful application of machine learning and the Open Catalyst Project OC20 dataset have for the future of renewable energy storage technologies and their adoption on a larger scale?
The successful application of machine learning, alongside the Open Catalyst Project OC20 dataset, holds significant implications for the future of renewable energy storage technologies and their broader adoption. Firstly, by enabling faster and more efficient identification of effective electrocatalysts, machine learning can help researchers discover new materials that are both cost-effective and high-performing. This is like having a powerful tool that allows you to quickly assemble a team of superheroes to tackle a challenging problem. With better catalysts, the processes involved in hydrogen and methane production can become more efficient, making renewable energy solutions more viable and attractive. Secondly, the OC20 dataset provides a vast amount of data that can help refine machine learning models. This data includes numerous simulations of catalyst interactions, which means that researchers can train models to predict how different catalysts will behave in a variety of conditions. Imagine having a huge collection of practice puzzles that teach you how to solve even the most complex ones. This abundance of information can lead to breakthroughs that might not be possible through traditional methods alone. Moreover, as machine learning models become more accurate, they can significantly reduce the time and resources needed for experimental testing. Researchers can explore many more combinations of materials and configurations without physically testing each one in the lab. This efficiency can lead to faster development cycles for new renewable energy technologies, potentially leading to quicker commercial availability. Lastly, by making renewable energy systems more efficient and cost-effective, there is a greater chance for these technologies to be adopted on a larger scale. This can help address global energy needs and contribute to reducing greenhouse gas emissions, supporting efforts to combat climate change. In summary, the combination of machine learning and the Open Catalyst Project OC20 dataset can lead to the development of superior electrocatalysts, driving innovation in renewable energy storage technologies and promoting wider adoption in the future.
Given the rapid advancements in machine learning and materials science, what future research directions do you see being most impactful for further enhancing electrocatalyst design and improving renewable energy storage solutions?
Future research directions that could significantly impact the enhancement of electrocatalyst design and improve renewable energy storage solutions include several key areas. 1. Advanced machine learning techniques. As machine learning continues to evolve, developing more sophisticated algorithms that can model complex chemical interactions will be crucial. This could involve using deep learning methods that can handle the intricate structures and behaviors of larger molecules, enabling researchers to predict the effectiveness of new catalysts with greater accuracy. 2. Exploration of larger molecules. Understanding how larger molecules interact with electrocatalysts is essential for improving the production of high-energy fuels. Future research could focus on modeling the interactions of these larger molecules, which often involve more complex bonding scenarios. This exploration could unlock new avenues for catalyst design that are currently not well understood. 3. Integration of databases and datasets. The ongoing development and refinement of comprehensive datasets, like the OC20 dataset, will be vital. Creating more extensive and diverse datasets will allow for better training of machine learning models, leading to more generalizable results and the identification of new materials that can serve as effective catalysts. 4. Real-time predictive modeling. Implementing real-time predictive models that can simulate and evaluate catalysts during experimental processes could streamline the development phase. This approach would allow researchers to quickly adapt and optimize their designs based on continuous feedback from these models. 5. Interdisciplinary collaboration. Collaborating across different scientific fields, like materials science, chemistry, and computer science, will foster innovation in catalyst design. Bringing together diverse expertise can lead to novel approaches and breakthroughs in understanding and improving electrocatalysts. 6. Sustainability and cost-effectiveness. Focusing on the sustainability and cost-effectiveness of new catalysts is important for large-scale adoption. Research could aim to discover abundant and low-cost materials that can replace expensive noble metals, which would make renewable energy solutions more accessible and practical for widespread use. In summary, pursuing these research directions can lead to significant advancements in electrocatalyst design, ultimately enhancing renewable energy storage technologies and fostering their adoption on a larger scale.
Thank you all for joining us today. We've explored the fascinating world of electrocatalysts and their role in renewable energy storage. We've learned that electrocatalysts enable efficient electrochemical reactions in renewable energy storage. Researchers strive to find low-cost and efficient electrocatalysts for scalable renewable energy solutions. Machine learning, aided by datasets like OC20, accelerates electrocatalyst discovery and design. This has promising implications for the future of renewable energy storage, more efficient and cost-effective systems, wider adoption, reduced greenhouse gas emissions. Future research directions include advanced machine learning techniques, exploring larger molecules, integrating databases, real-time modeling, interdisciplinary collaboration, and a focus on sustainability and cost-effectiveness. We're grateful for the insights shared by our esteemed guest. Let's continue exploring and innovating in this exciting field. Thank you.